Dear students, in this session I am going to discuss about the cells. In physics, cells means it is the source of energy. You may go to a shop and purchase a battery cell whose value means in the sense its potential difference mentioned it is 1.5 volt, and there will be mark also plus and minus that represents the positive terminal of the cell and negative terminal of the cell. Okay, so in almost all many devices, electronic devices, it may be your mobile also, there will be a cell inside it. There is a battery, okay, with the plus and minus connections will be there. So it has got some potential difference, maybe 4 volt or 5 volt. Okay, then we see in the torch also, there also we need a source of energy. It is nothing but a combination of cells. There may be 2 cells or 3 cells joined in combination, series combination actually. So that gives you more potential difference across the combination, series combination. So cells are used in most of the circuits where DC cells. Okay. Now AC means in household circuits all we use AC, alternating current, whereas in our devices like mobile or a torch, okay, all this what we use it is DC cells. Okay, direct current. They produce a current which is almost constant in magnitude, which drives a constant current through a given circuit component or a resistor or a bulb. But after a long time usage, the potential difference across the cell or EMF of the cell may slightly decrease. Okay, because the charges gets neutralized continuously, so it is called discharged. And then the basic arrangement of cell is very simple. It is a cell has 2 electrodes, positive electrode P and negative electrode N. Positive here I have written plus and negative I have written N, negative. And the two electrodes, positive electrode and negative electrodes are dipped in the electrolyte or electrolytic solution. This is the basic arrangement in a cell. Okay, in our dry cells, what we use in the torch or in mobile, it is dry cell. In the inverter arrangement, we have liquid cells where the ions, okay, they're in a liquid. Okay, ions are dissolved in the liquid. Whereas in dry cells, there may be a powder, okay, or certain substances are used. Okay, nickel, cadmium, etc. Now, in whatever the type of cell, dry cell or liquid cell, electrolytic solution type of cell, there will be 2 electrodes and liquid or the surrounding medium. Okay. Now, okay, so coming to this point here, whenever the electrodes are dipped in electrolyte or electrolytic solution, the electrode exchange charges. Okay, so positive electrode will have positive ions on it and the negative electrode will have negative ions on it. Hence, there will be potential difference between the positive electrode and immediate surrounding point in the electrolyte. Okay, so this point, if I take a point A very close to the electrode in the electrolytic solution or electrolyte substance, so that point and the positive electrode will have a potential difference. So that I will take V plus. Okay, V plus is the potential difference between the electrode, positive electrode, and the immediate point or surrounding point in the electrolytic solution or electrolyte, that is V plus. And next, that is the potential difference or potential developed by the positive electrode because of positive ions present in it. Whereas the negative electrode will have a potential, okay, so minus V minus, because only negative ions are present in the present on the surface of the negative electrode. Okay, so potential on the negative electrode will be negative. So minus V minus. Actually, V minus is a positive number. Okay, this is positive number. V minus means certain 5 or 3 or something like that. Okay, then potential on electric potential on the negative electrode is minus V minus. This V minus is a positive number. So like minus 3. Here it may be plus 5. Here it may be minus 3. Okay, so like that. So negative potential is developed on the negative electrode with respect to the immediate surrounding of the electrode, negative electrode. So the potential difference is minus V minus. And then whenever the circuit or the cell is open open like this, there is no external connection in the cell, the potential throughout the electrolyte will be same potential, as there is no current flow. Potential throughout the entire electrolytic solution is same, and no current flowing from A to B or B to A. And the potential difference across the terminals of this is called as EMF. Okay, EMF denoted by symbol epsilon. EMF is the potential difference. So first definition here, basically a cell is a source of energy which supplies the current whenever connected to external circuit. When the circuit is closed, then there will be current in the current can be drawn from the cell through that external component. It may be a bulb, or it may be any resistor, any heating element, or any circuit element. So when it connected, it will give, the cell will give the energy in the form of maybe light or heat or anything, or mechanical type of energy also. Okay. So then next, the potential difference across the terminals of the electrode when no current is drawn from the electrode is called as electromotive force. It has nothing to do with the term force. It is not a force actually, but okay. But while naming, it is given like electromotive force. Hence we have taken from long back. It is not the recent term. It is a long back term used. So nothing to do with the force term here. It is not a type of force. It is a potential difference. Electromotive force is the potential difference across the terminals of the cell or a battery when no current is drawn from the battery, or when it is in open circuit. Now this arrangement, it is open circuit of a cell, or when you take a cell or a battery from the shop, it is open circuit. You are not connected to any of the devices. But when you put into a torch and put the cap, then you press the switch, then circuit becomes closed, and you can see the effect. That is, there will be light. Okay. From the torch we get light. From where light comes, that is the electrical energy which makes the bulb to glow, and it is energy stored in the cell as a chemical form. It is a chemical energy stored in the cell. When it flows, it is called electrical energy, and finally we get light energy from the torch. Okay, so that is the idea of a cell. A cell is the basically source of energy. Okay, so that energy can be used for any purpose. Okay, so now these cells are extensively used in many purposes, electronic devices, even the meters also. Nowadays digital devices, we use these cells. Okay, in the voltmeter, ammeter, all that also we use the cells. That is, in multimeter we use this kind of cells, and in the experiments we use some kind of cells, like meter bridge experiment, all that we use the simple dry cell. Okay. So electromotive force is a term related to the cell that says the potential difference. But EMF or electromotive force is the potential difference across the terminals of a cell. Simply if I put a diagram like this, okay, this is the plus and this is minus. Okay, this is minus. So potential difference across the terminals of a cell between these two. Okay, when no current is drawn from the cell, or when the cell is in open circuit. When cell is in open circuit, the potential difference between the terminals is EMF, is the EMF of the cell. Okay. Next, this EMF determines the ability of the cell. Okay. Then there is another term called internal resistance. Internal resistance of a cell is the effective opposition for the flow of charges or current or resistance provided by the electrolyte of the cell. Okay, electrolyte of the cell provides some opposition. So whenever the circuit is closed, that means some external resistor or some external component when we connect in a circuit, then charges starts flowing, and in the external circuit, remember, only the electrons will flow. That is conducting path. So whenever the electrons flow, or when there is a current set up in the circuit by means of this cell, with the help of this cell, then okay, there will be opposition for the flow of charges within the electrolyte. So electrolyte also produces certain opposition. Okay, so then that opposition caused by, or resistance caused by or produced by the electrolyte of the cell for the flow of charges through the cell is called as internal resistance of a cell. Okay, that is denoted by small letter r. Okay, small letter r we use, and this is EMF symbol epsilon. Okay, then one more term related to the cell is terminal potential difference, or it is shortly called terminal PD, and denoted by symbol capital V. Okay, terminal PD of a cell is what? Now this is in cell in open circuit. Now the symbol of the cell I can write like this. Symbol of a cell. Okay, this is the electrode, positive and negative electrode. Normally we show in the books and all. Okay, but actually we the cell we show interresistance also. Okay, in your textbook, that is in NCR textbook, we have not shown they have not shown the interresistance part. You can ignore also. You can write also. Sometimes you can write epsilon r like this also. Otherwise you can write epsilon here and interresistance r. Okay, this representation is also okay. This representation is also okay. But here I write epsilon and comma r separated by comma. So that means a cell with the EMF epsilon and interresistance r. Now when I connect a resistor, okay, what happens? There will be current in the circuit. That means a current flows in the resistor. Okay, so there will be opposition caused by external part, that is external resistor r, and also internal resistance small. Interresistance smaller and external resistance capital. Now the terminal PD, okay, the potential difference across this cell, okay, terminal PD across this cell when current is flowing in the cell is called as the terminal potential difference. Potential difference across the terminals of the cell, okay, this or this, when current is set up or current is flowing through a cell is called as terminal potential difference. So EMF and terminal potential difference are expressed in a unit called volt. Remember it is small v, and symbol is capital V. So volt is the SI unit of electromotive force or terminal potential difference. Okay, and interresistance is expressed in units of ohm, and here O is small letter and symbol omega. Okay, so this is the symbol for internal resistance. Interresistance will be practically it is very small value, maybe less than ohm sometimes, but in problems, when solving problems, sometimes we consider the interresistance whenever the problems given with the data with interresistance. If they have not mentioned in any problem, or sometimes they give negligible interresistance, we put the value of interresistance small or equal to 0. Okay, so that's all about the three terms. And a cell. Cell is a source of energy which drives the charges in any circuit. Okay, so depending upon the ability of the cell, if you join the cells in series, obviously the potential difference increases and we get more current in the cell. Okay, so then next I will discuss the current drawn by this cell when connected to some external resistor. So it is the expression, derivation of expression. Derivation of expression, this is important derivation in this chapter. Expression for the current drawn from a cell. Current drawn from a cell when connected to external resistor. When connected to an external resistor. Okay. External resistor. Okay, this is the expression we have to derive. Now for this we consider a simple cell. Okay, simple cell I will take. Okay, no need to mention internal resistance outside the cell. We understood that it is there, interresistance. Consider a cell of EMF epsilon and interresistance small, and positive terminal is the longer line and the short small line represents the negative terminal of the cell. And then we have one external resistor we connect. The resistance opposition, this zigzag we show, that is external resistance. Now we have to get the expression for the current drawn from the cell here, and the current flowing in the external resistor is also I only. So this is the current which is flowing like this. Okay, the current flow is a clockwise direction, and actually electrons flow in the anti-clockwise direction. And the EMF of the cell is epsilon, internal resistance is smaller. Okay, then the terminal PD of the cell or potential difference across the terminals of the cell. If if I take a terminals of the cell A and B, okay, here I will complete that circuit. Okay, here I put a resistor, external resistor R, okay, external resistor R, and EMF is here actually. But when cell is complete, the circuit is completed by connecting a resistor R, then the current will flow like this, positive terminal, and it will flow like this, and this potential difference is not EMF. When it is open circuit, potential difference across the positive and negative terminal is EMF. When it is a closed circuit, when external resistor is connected, the potential difference across the terminals of the cell is V. Okay, that is a terminal PD. Now this is the circuit for that derivation. Okay, now from this part, whenever there is no current flowing or current drawn from the cell, the EMF is the potential difference between the two electrodes. Okay, so EMF of the cell, potential difference between the two electrodes, that is EMF equal to potential difference between the two electrodes, means potential of the positive electrode with respect to immediate neighboring electrolyte point, say A, at a point on the electrolyte A, that is V plus. Then potential difference between A and B is 0, no potential difference, because some entire potential is same within the electrolyte. Potential difference between A and B is 0 when in open circuit, when no resistor is connected. So that point is that potential difference 0 between A and B. And now between B and negative electrode, the potential difference is minus of minus V minus. And remember, V minus, this number is a positive value with the one minus and outside minus. So we can write V plus plus V minus. So this is the EMF of a cell when it is in open circuit, means no external resistor connected. Now when external resistor is connected, a current I flows through the external resistor as well as in the electrolyte. Through the electrolyte also same current I flows. Okay. Now the potential difference, okay, this is in open circuit, I have to say, in open circuit. In open circuit I say it is EMF. Now when external resistor is connected, when it is closed circuit, okay, when it is closed circuit, okay, the current potential difference across the terminals of the cell we have to find out. Okay, now again the potential difference across the terminals of the cell, okay, PD, okay, potential difference or potential drop, potential difference across the terminals of the cell, potential difference across the terminals of the cell, say V, it is shown here V, when it is connected, external resistor is connected, V is the PD. Now potential difference between the positive electrode and negative electrode, effectively how much? Potential of the positive electrode is V plus with respect to the immediate surrounding electrolyte. Then there is a current now. In the external circuit also current I is there, in the internal resistance also there is current. Okay, through the internal resistance also there is current. Internal resistance is the effective opposition offered by the cell. There is a current, and that current we take I, and the potential difference between the points A and B is minus IR, okay, minus I into R. Okay, the current flow is this way, we are going from A to B, so the potential difference is minus IR between A and B. Then next plus, okay, or minus of minus I, right, minus of minus V minus. This is the potential difference between the point B and the electrode, negative electrode. Point B and negative electrode, potential difference is minus or minus V minus. So this is equal to, okay, so V plus plus V minus, V plus plus V minus, then minus IR, minus IR. So I can write this potential difference or terminal PdV equal to, potential difference or terminal PdV equal to, terminal PdV equal to, now V plus plus V minus is nothing but EMF epsilon, EMF epsilon minus IR, EMF minus I into R. Okay, So then next this is equation 1 I take. Now external resistor, current flowing through external resistance is I and resistance value are from Ohm's law. Okay, from Ohm's law. The terminal PD of the cell also we can say here for external resistance I say PD across external resistance. Okay, PD across R is equal to between these 2 points, say points I can take A and B. Okay, A and B. PD across A and B, so that is V equal to I into R from Ohm's law, equation 2. Okay. Now comparing the V equal to, this is first part for the cell, potential difference across the cell when current is flowing is EMF minus IR. When external resistor is connected, there is a current flow in the external resistor also. So potential difference across the external resistor or potential drop across the external resistor is V equal to IR. Now comparing these two, we can write, okay, so IR equal to, from equation 1 and 2, from 1 and 2 or comparing 1 and 2, we can write IR equal to epsilon minus IR. IR equal to epsilon minus IR. So bring minus IR to the LHS. So IR plus IR equal to epsilon. Okay, so then last part I do it here. So I is common here. I is common. Okay, so R plus R remains, okay, equal to EMF epsilon. Hence, finally, I equal to current I equal to epsilon divided by R plus R. Okay, so this is the final expression for the current drawn from external resistor or current drawn from a cell, current flowing through the external resistor which is drawn from the cell when an external resistor connected to a cell. Okay, so one cell is there whose EMF is epsilon and has got its internal resistance smaller, denoted by smaller, and external resistor of resistance R is connected across the cell. Okay, so positive terminal to one end, negative terminal another end. So there will be a current I drawn from the cell and the same current flows through the external resistor R. Okay, so then first we write the EMF of the cell. EMF is the potential difference across the terminals of the cell when no current is drawn from it. Hence epsilon, EMF epsilon equal to V plus potential difference across A and B is 0 when no current is drawn, and minus of minus V minus. So EMF is V plus plus V minus. Okay, so then potential difference across the terminals of the cell or across the external resistor when current is drawn from the cell. Okay, when external resistor is connected across the cell is, it is also called as terminal PD, is V equal to V plus minus IR minus R minus V minus. So this term V plus plus V minus is EMF epsilon. So V equal to epsilon minus IR, that I take as equation 1 for the cell, terminal PD across cell. Okay, so then next from Ohm's law, the PD across the external resistor R is V equal to IR, equation 2 I take. Comparing equation 1 and 2, terminal PD across the cell or the potential drop across the resistor, both are same. So IR equal to epsilon minus IR, bringing minus IR to the LHS. IR plus IR equal to epsilon, that is EMF, and I is common in both the terms. Taking out, we get I times R plus R equal to epsilon, that is EMF.